right now, your computer is essentially this brilliant but incredibly fragile idiot.
Oh, absolutely.
I mean, you give in and update the operating system, assuming, you are just securing your machine. But the moment one single line of code in that new update conflicts with, like, your audio driver, the whole system just throws its hands up.
Yeah, it just panics.
Right. It drops this cryptic error code on the screen and literally just waits for you to save it. And you end up spending, hours scrolling through obscure tech forums on your phone, hunting for some random terminal command from 5 years ago just to fix the thing the update broke.
Which is wild when you think about it.
It really is. But what if your operating system actually had a survival instinct? Like, what if it could realize something was broken, hunt down the solution, apply it, and make sure that specific failure never happened again?
It fundamentally changes our relationship with our hardware. I mean, we are so conditioned to view the operating system as this static, brittle layer of software that just executes commands until it hits a wall.
Right.
But the paradigm shift we are looking at today moves us away from that fragility toward a genuinely autonomous, self-sustaining system.
And that is the core mission for this deep dive. We are looking at a stack of notes centered on an August 17th, 2026, LinkedIn Pulse article by Maurizio Rossari. The piece is called From a Base System to a Self-Healing Operating Model.
Yeah, it's a fascinating read.
It is, and it details this massive architectural shift driven by a project called syrag-pi-tools. And right from the jump, I think we need to be clear that this isn't just, a standard-based system with a new troubleshooting wizard glued to the desktop.
Oh no, slapping diagnostic tools onto an old architecture doesn't change the underlying reality that the system is completely blind.
Right.
Because traditional diagnostic tools are reactive, They wait for a human to trigger them, they run down this rigid if-then checklist, and if the problem falls outside that narrow list...
It's just fail.
Exactly, they fail. The architecture outlined here is built from the ground up to autonomously detect anomalies, write repairs, verify the physical mechanics of that repair, and retain that knowledge permanently. The system doesn't just run, it actually learns.
Okay, let's unpack this. Because to understand how a system heals itself, we have to understand how it observes itself in the first place, right?
That's the foundation.
Because a traditional OS doesn't really know its own state. It just knows if a process is running or crashing. syrag-pi-tools flips that by introducing a module called syrag-pi-tools.
Right, the Pi-tools module.
Yeah, and this module basically gives the operating system an AI agent with practical operational capabilities. So instead of a car that just flashes a vague check engine light and leaves you stranded on the highway...
Which is the worst.
This is like having a tiny live-in mechanic under the hood who can actively inspect the engine, diagnose the misfire, and actually start turning wrenches while you are still driving.
I love that analogy. And let's look at the technical reality behind that mechanic analogy, because it is crucial. This syrag-pi-tools thing, it isn't a passive background service.
Okay.
It is a fully agentic framework that dynamically interacts with the system's environment. One of its main jobs is managing gateway interactions.
Right, like how it talks to the outside world.
Exactly. In a standard setup, your machine is constantly communicating with external gateways like API endpoints, cloud services, authentication servers. If an external provider goes down, a traditional system often just panics.
Yeah, you get the endless spinning wheel.
Right. It might block the boot process entirely, hanging on a loading screen just because it can't reach one specific server. The syrag-pi-tools agent intercepts that failure.
So it sees the panic happening.
Yeah, it understands that the gateway is unreachable, gracefully degrades the service, caches the local policy so you can actually keep working, and then it continues polling in the background without locking up the user interface.
So it adapts to the outage instead of just surrendering to it. And the text notes this agent can integrate with both local and external AI models. So wait, it isn't just relying on a remote cloud server to tell it what to do.
No, not at all.
So if you're completely offline, the local model is still monitoring system health and managing those internal operations.
Yes, and that local capability is what makes the self-healing aspect genuinely viable. I mean, it allows the machine to reason over the system as a live, fluctuating environment.
Right.
It doesn't halt your workflow for some temporary network blip. It dynamically reroutes or pauses services based on real-time operational context.
But okay, there is an obvious physical problem here, I think.
Okay, what's that?
If this live-in mechanic is constantly turning wrenches, tweaking system settings, and adjusting drivers on the fly, how does it know what to fix without accidentally breaking something else?
That's the million-dollar question.
Right, because if I go into my system settings and start experimenting, half the time I make things way worse.
Well, sure, but The agent doesn't experiment blindly. It operates using a very specific knowledge base. This is essentially the operational memory of the system.
The living memory.
Yeah,
The syrag-pi-tools knowledge base stores verified fixes for real-world issues, and the sources actually give some very specific examples of what this handles in the wild.
they do, yeah.
We are talking about hardware-specific audio problems, gateway security concerns, boot failures, recurring system regressions, and FIPS-related findings.
FIPS findings are a perfect example of why this autonomous memory is so valuable.
Wait, let's pause there. For those of us who aren't enterprise compliance officers,
Yeah.
what exactly does a FIPS finding mean for a machine, and why is it so hard to fix normally?
Good question. So FIPS stands for Federal Information Processing Standards. It is a set of incredibly strict cryptographic rules used by government agencies, highly regulated industries, places like that.
Okay.
If an operating system uses a hashing algorithm or an encryption protocol that isn't FIPS compliant, it gets flagged. That's a FIPS finding.
Got it.
In a normal enterprise environment, fixing a FIPS finding means a system administrator has to manually comb through configuration files, identify the non-compliant encryption cipher, rewrite the config to force a compliant cipher, test it to ensure the application still communicates, and then deploy that fix across maybe 1,000 machines.
That sounds miserable.
It is. It's incredibly tedious, error-prone work.
And Syragos automates that. Like, the AI agent detects the non-compliant cipher, swaps it for a compliant one dynamically, and logs the fix.
Exactly.
But I have to push back here hard.
Go for it.
We are talking about AI models executing system-level changes. I mean, I have seen AI confidently write code that doesn't even compile. I've seen it hallucinate basic facts.
Sure. Right.
So if this agent misdiagnoses an issue and just hallucinates a fix for my network driver, it doesn't just fail, it completely bricks my Wi-Fi.
Yeah.
How do we know this thing isn't just confidently destroying the operating system based on a bad algorithmic guess?
What's fascinating here is the distinction between generative guessing and deterministic verification.
Okay, tell me more.
The agent isn't an LLM just spitting out a creative terminal command and hoping for the best. When it encounters an anomaly, it checks its condition against the known rules in the knowledge base.
Right.
If it formulates a fix, it does not just commit that change to your live system blindly. It applies the fix in an isolated state and runs a rigorous verification loop.
Wait, walk me through that verification loop. How does the system physically prove to itself that a fix worked?
So let's use your Wi-Fi driver example. The agent applies the patch. To verify, it doesn't just check if the code compiled. It actually runs a localized ping test to a known stable IP.
Oh, wow.
Yeah, it reads the system DMS logs to look for kernel panics or driver timeouts. It checks the exit status codes of the networking daemon.
So it's looking at the actual physical results of the code.
Exactly. If the ping fails, or if the daemon returns a fatal error code, the agent immediately knows the fix failed.
And then what?
It rolls back the change using a snapshot before this system state is ever permanently altered. It only records the outcome into the knowledge base, becoming permanent operational memory if every single verification check passes.
So it is a closed factual loop. It tests its own work against physical reality like, did a packet actually reach the router? And if the answer is no, it reverts.
Yeah.
It is building a permanent library of factual resolutions, not statistical guesses.
It is building an operational truth. And this solves the nightmare of recurring system regression.
Oh, regressions, yeah.
Think about how often a software vendor releases an update that accidentally reintroduces a bug they fixed 6 months ago.
That happens all the time.
Right. With Syragos, once a node resolves an issue and verifies the fix, that resolution is locked in.
Oh, I see.
If a new update tries to regress the system, the agent instantly recognizes the failure signature, pulls the verified fix from the knowledge base, and applies it before you even notice the regression.
Okay, so we have this incredibly smart agent that diagnoses issues, rigorously tests its own patches, and remembers them forever.
Yep.
But if this OS is constantly self-healing, applying patches in the background and updating its own core rules, how does it do all that without accidentally wiping out my family photos or my work documents?
That is the big concern.
Because if the system has to hesitate because it is terrified of deleting user data, it can't truly heal itself freely, right?
You've hit on the physical limits of self-healing. All of this intelligent troubleshooting is completely useless if the underlying structural architecture is brittle.
Right.
You cannot have a dynamic, self-healing software layer if the foundational file system cannot handle continuous radical change.
And here's where it gets really interesting, because the system uses a second core module called syrag-iso-builder to solve this exact problem.
Yes.
This is the installation and build layer. It takes a chosen base environment and turns it into a usable syrag environment. And they note that it is deliberately distro-agnostic.
Which is huge.
Yeah, right. The base system, whether it's Debian, Arch, or Fedora, is just a deployment choice. It isn't hard-coded. But the real magic is the split partition model.
The structural separation of data.
Exactly. To go back to our earlier analogy, it is like building a house where you can demolish and replace the entire foundation, the plumbing, and the electrical wiring, which represents your system configuration and the runtime state, without ever touching the living room furniture, which is all your personal user data.
I like that.
It physically walls off the user from the machine's internal experiments.
Let's translate that house analogy into Linux architecture, because the mechanics of how this works are brilliant.
Please do.
In a traditional operating system, your system files, your applications, and your personal data are often tangled together on the same primary partition.
Right, it's all just one big drive.
Exactly. If an update corrupts a core library, rescuing the system often means wiping the drive and starting over, risking your data. Syragos employs an immutable root file system.
Meaning, the core operating system files literally cannot be altered by normal user applications.
Right. During runtime, the root partition, where the actual brain of the OS lives, is mounted as read-only.
Oh, wow.
The system uses overlay file systems for any temporary state changes. Meanwhile, the home directory, which holds all of your documents, photos, and personal configurations, lives on a completely separate, mutable partition.
Okay, I see where this is going.
So when the syrag-iso builder deploys an update, or the AI agent needs to completely rebuild a system state to recover from a massive failure, it can overwrite its own core binaries on reboot.
It can literally swap out the entire foundation of the house.
Exactly, and it never even crosses the boundary into your home folder.
So the system can be entirely destructive to itself in the pursuit of healing without ever putting the user at risk. That is such a vital design choice.
It really is.
And the sources also mention that the syrag-iso builder manages a very specific deployment flow to prevent issues from ever reaching the user in the first place.
Yes, the build flow.
Right. It validates prerequisites, installs the base stack, applies those recovery fixes we talked about earlier, and then packages the final image for boot testing.
And that boot testing phase happens before the user ever interacts with the final installation.
Okay.
It incorporates the validated remediation from the knowledge base directly into the next system image.
So we go back to that scenario from the very beginning of our deep dive. You click Update.
Right.
But instead of rebooting to a broken Wi-Fi driver, the syrag-iso builder does all the heavy lifting in the background. It builds the new image, applies the operational memory of past fixes, tests the boot process, and makes sure that when it hands the keys back to you, everything just works.
The security checks are baked into the deployment path from the start, rather than being treated as a desperate afterthought when things break.
When you combine all of these elements, you get a closed operational loop. Detect the anomaly, fix the issue, verify the physical result, learn the outcome by writing it to the knowledge base, rebuild the system image securely.
That is the life cycle of a modern, resilient machine.
So what does this all mean? I mean, it means we are moving away from the era of shipping a customized OS image, crossing our fingers, and hoping it magically works on every combination of hardware out there.
Thankfully.
Syragos treats software as a living, evolving entity. It absorbs the complexity and the chaos of the real world so the end user doesn't have to. But the project isn't stopping there. The sources point to the horizon. And the system isn't just learning in isolation on one single machine. They are moving toward a distributed delivery model.
This is where the architecture scales from individual resilience to network-wide resilience.
Right.
The documentation specifically highlights the integration of IPFS for artifacts and resource distribution.
IPFS being the interplanetary file system.
Yes.
Now, for those who might only know how standard web servers work, how does IPFS actually change the way a computer gets its updates?
So the standard internet uses location addressing. When your traditional OS wants an update, it goes to a specific URL like a specific server in a specific data center and asks for a file. If that server is down, or if the network is highly congested, you don't get your update.
You just get an error.
Exactly. IPFS uses content addressing. It doesn't care where a file is located, it cares what the file is.
Oh, interesting.
Every piece of data is given a unique cryptographic hash. When your Sargos node needs a new system image or a verified fix from the knowledge base, it asks the decentralized network for that specific hash.
Wait, so it's not going to one central server?
No, it can download fragments of that update from 5 different peer nodes located right next door to you, rather than relying on one centralized server halfway across the globe.
It is a peer-to-peer swarm for system updates.
Yeah.
If a centralized server goes down, the network doesn't even flinch because the nodes are sharing the resources among themselves. That fundamentally changes how resilient the whole ecosystem is.
It does.
But the source material is very upfront about where they currently stand with this, right?
Yeah, if we connect this to the bigger picture, the architecture is not pretending to be a fully decentralized utopia today.
Right. They aren't there yet.
The integration of IPFS and distributed delivery is described as a progressive move. You don't just flip a switch and instantly decentralize an entire operating system.
Of course not.
You design the capacity for distributed delivery into the foundation from day one. You build the immutable root file systems, you isolate the data, and you standardize the knowledge base.
Doing the groundwork.
Exactly. By doing that, you reduce central dependency step by step, increasing portability and resilience over time, so that as the project evolves, it seamlessly transitions into that peer-to-peer model.
It is a pragmatic architectural march toward decentralization.
Very much so.
So let's bring it all home. We have journeyed from the static, fragile operating systems we all tolerate to this dynamic, self-healing model.
Yeah.
We have an AI agent embedded through syrag-pi-tools acting as a live-in mechanic that dynamically handles gateway outages and FIPS findings.
Which is huge for compliance.
Huge. We have a knowledge base that serves as a permanent operational memory, rigorously verifying its fixes through ping tests and exit codes so it never hallucinates a bad patch.
Right.
We have the Syrag ISO builder, leveraging an immutable root partition, allowing the system to completely rewrite its core files without ever touching your personal data.
Protecting the user.
Always. And we are looking at a progressive evolution toward IPFS and distributed, decentralized delivery.
The machine takes on the burden of its own maintenance. I mean, it fundamentally redefines the contract between the user and the operating system.
It automates the frustration out of existence. But before we wrap up this deep dive, there is one final puzzle piece to think about.
Yeah, and this raises an important question, especially when we look at that fully distributed horizon.
Okay, what is it?
The end goal is a decentralized, self-healing network where future nodes inherit the operational memory of past fixes. But what happens when two completely independent Syrag nodes sitting on opposite sides of the world discover a brand new, unprecedented bug at the exact same time?
Oh.
Right. They both run their verification loops. They both find a fix. But they come up with completely different verified fixes that both technically work.
Wait, so which one wins?
That's the question. How will an entirely decentralized system negotiate which truth to adopt into its permanent memory?
That is a brilliant puzzle and definitely something to ponder the next time your fragile traditional OS locks up your screen and demands a restart. Keep questioning the systems you use every day, and we'll catch you on the next deep dive.